I wanted to show you one thing before we wandered off. I put this video on our Canvas page. This is a boomerang filmed in slow motion. Notice the shape of the boomerang looks like a Greek letter omega. Let me pause that right about there. The motion of the boomerang itself rotates around this point, which is not actually part of the boomerang. That's the center of mass. If you watch the boomerang itself turning, its internal, its rotation itself is around the center of mass of the object, which isn't actually a point in the object. You would think it would spin around the top of the arc there, but it doesn't. It spins lower than that. Between that and the shape of the airfoil edge, that's what allows it to curl back in. The usually 20-degree lip on the edge there. But you've got this video in our Canvas page to play with at your leisure. Meanwhile, on to a couple of different applications. So let's take a look at some economics applications, some biology applications. I'm going to start with economics. Anybody taken an econ course of any type? Tell me about supply and demand. Whatever you know. Neil?
Supply and demand, like supply goes up, and the demand goes down, like that.
Not necessarily. Supply and demand are usually two different sides of the same transaction. So they're kind of independent of one another. When supply goes up, we have more of whatever it is. It isn't that demand goes down.
We go up in demand.
It depends. Prices tend to go down. If you have more of something, it's easier to buy, right? So it should be cheaper. That's why, disposable lighters are less than $1 and Ferrari Testarossas are more expensive. So I think of quantity and price as being related. Now, personally, I hate the econ people for doing this, but they made quantity the independent variable and price the dependent variable. So when you have more of something, price goes down. So I have a curve that, well, even if I just had a straight line, which is not necessarily realistic, but I could think of something like this. And this is a supply curve. Price is some function of quantity. On the other hand, human beings are cheap. Maddie, can I pick on your grandma? She bought those generic from Sam's Club because they were cheaper, right? Okay. So as stuff gets more expensive, people don't want to buy as much of it. So as price goes up, quantity desired goes down. Unless we create some other connected confounding variable, like something is a status symbol, something is an expensive investment item. I'm going to have to pull a marketing piece from the late 80s, and I apologize to you all. Bourbon is really expensive nowadays. Do you know why bourbon is expensive nowadays? Because two companies decided to try and make bourbon a status symbol. And Maker's Mark in sometime between 90 and 2000 said, no, our bourbon is going to be more than Jack Daniels and Jim Beam. It's more expensive. It's a better product. We're going to charge more for it. We're going to link that to quality. Now, I don't particularly care for Maker's Mark. My dad drinks it. I don't care. But all of a sudden, there was a new confounding variable to price. I'm discounting that for now. I mean, I will tell you that about 20 years ago, no one on the face of the planet would have thought of buying a phone. You got one when you got your phone number and rented it from the phone company. It came with the house. So as prices are low, as prices go up, I did it again. As prices go up, fewer people want to buy stuff, right? As the price is expensive, there should be few sold. But as the price is cheaper, more and more are sold. What happened in Maker's Mark when they said, no, as a producer, we want to supply stuff. If you're only making $1 on each thing, do you want to make a lot of them or a few of them? Is it worth your while? Suppliers have this reverse idea. When they are getting very little money, they don't want to make a lot of whatever it is. It's more profitable to sell stuff when the prices are high. So supply side says, charge a lot, we'll make more money, therefore we should make a lot of those. Put your money into the most profitable product. Demand, I don't want to spend a lot of money if I don't have to. What do you see in the middle of that picture? Somewhere there's a balance point. It's called the market equilibrium point. And there's an equilibrium quantity and an equilibrium price. At that point, everything that the suppliers make gets sold. And every person who's willing to buy at that price buys one. That is the ideal market environment. Everything goes out, gets sold, everybody is happy that purchased it, they were happy with the price they got. On the other hand, there were people who were willing to save, to spend a little more, right? Demand. There were fewer people who were willing to spend a little more. So by holding out until the price got lower, those consumers, the demanders, they saved money. Let's apply a couple numbers here. I'm going to call this equilibrium price capital P, and I'm going to call this equilibrium quantity Q0. I think the book may use X's instead of Q's. If it does, I apologize. Just change all my Q's to X's, and we're good to go. The amount of money that the people who were willing to buy at a higher price saved is an integral. every person between 0 and Q0 would have paid more money. They're on this part of the demand curve. But they didn't pay this much money, they paid this much money. So the amount they saved can be determined like this. That's the top curve minus the bottom curve, right? Area between curves, chapter 6, section 1. We did this. I'm just applying it. But I want the total from all of those people. That means I need to add up all of that money. This is called consumer's surplus. And it's additional money still in the economy available to do other things. That's money that these people would have spent on this product, whatever it is. But they didn't have to because the price was lower than they were willing to pay. But there's another area and a flip side to this same idea. Let's think about the supplier's perspective. They made more units and sold them at a particular price here. If the price had been lower, they would have produced fewer, right? They wouldn't have made as many. They made more quantity because of where the price was. So if we think of this difference, what does that represent in this economics setup? I don't know what you mean by other side. But these are producers, these aren't purchasers. These are makers, these are buyers. Oh, no, I'm not over here, I'm still over here. That's money that the supplier made for making more product, right? This is more, they were willing to make less, but since the price was high enough, they made more stuff. And they earned extra money than they expected. From the flip side, again, the same integral, adding up all of these additional purchases, we get producers surplus. Now this is where you have to start taking some economic theory and some potentially politically motivated discussion ideas here, because you could say, from a supply side economics perspective, this is money that I missed as a supplier. People were willing to spend it and I didn't get it. What do I do to get that money? Or as a consumer advocate, you could say this is money the producers took in as extra profit that they could have lowered the price and we would have been okay, us people up here. And this is where you start to get debates in politics on better fiscal policy. This is not a class on fiscal policy. Go talk to Dr. Warfield, Dr. Mahady, and the rest of the econ department, Dr. Vlad. They will give you all of the background in that direction. I can do the math. I don't know the politics side of this at all. So let me throw one at you as an example. We have a supply curve, a demand curve. Why do I know this? I didn't even write it in my notes, but why do I know this is a demand curve, not a supply curve? Going down. As quantity gets up, prices get lower. Let's just arbitrarily establish a sales level. Now, maybe this is my sales manager's target. This is how many units you should be moving every week, month, quarter, year. I don't know. I don't know what we're making. Maybe it's how much you should be moving every hour. We're in a movie theater selling buckets of popcorn. Or this is how many you should be moving every year. We're in the Bugatti factory selling variants. I sell 30 Bugattis a year. I'm making bank. I need one other piece of information not in evidence to figure out consumer surplus. What is the other piece of information I need? I need that price, that capital P in my equation up here. I have my function, which I called little p of q instead of f of q. That's price at a given quantity. That's my f of q equation. But I don't have this capital P price. How do I find it? I promise this is easier than you think it is. That's the point where the two meet. I have the sales value, the sales level. I just need the corresponding actual price. Again, I don't have units on this, so to what? I don't know. I think a cheap Bugatti might be $200,000. So, in order to find my consumer surplus, I integrate from where to where?
You want to integrate from 0 to 30.
Yep. And then my price equation minus my equilibrium price. Now, I will freely admit, this is a trivial integral because I picked a straight line equation. Here is a statement that I do not mean to sound disparaging, but will quite a bit sound disparaging. A lot of econ books I looked at never use anything except straight lines. It pisses me off to no end. Because most real models aren't straight lines. And a lot of the reason for that is because they don't want to do calculus. And that's just lazy, people. That's an easy integral. What's the answer here? Leo?
It would be 3 cubed. And it would be
Oh, you're walking me through the integral. Let me do the algebra then. 5 minus 2 is 3 minus q over 10 dq. So I get 3q.
we wanted 20 cubed squared.
Evaluated from 0 to 30. 30 squared is 900. So this gives me 90 minus 1/20th of 900. That's 90 over 2. That's 45, whatever it is. From a producer's standpoint, this means that when I set my sales level at 30 and my target price at 2, I'm leaving in the purchaser's hands 45 whatevers, money I could have gotten if I'd set the price a little higher, made a little less. It would have cut down how much money is still out there. Again, that's a fiscal policy decision, not necessarily a calculus decision. The more realistic models involve exponentials, logarithms, seasonal variability in prices. What has happened? Anybody drive? Who's got a car? What's happened to gas prices in the last 6 weeks? The last 6 weeks, they've gone down. It was 380, 390, and they're like 350 this morning. Gone down a bit. Why? It happens every year, the end of September, beginning of October. Why? The pipeline shipments and such? No, this isn't a pipeline issue. This isn't a shipping issue at this point. This is a change in formula. We went from summertime gas to wintertime gas because of the environmental changes of the amount of heat in the atmosphere. We switched the formula in gasoline, and winter gas is cheaper. Not a lot, but enough to have a market effect. So if I really want to bring that piece of information in there, then there should be a little bit of a trig function floating around for seasonal variation between summer and winter. The more accurate my model is, the more complicated this equation is going to get, and thus our integral is going to get nasty. Then we need all of our integral tricks. But my goal here is not to say, here's a really shitty integral, let's go do this one. My goal here is to say, hey, look, here's a real economics, modern, accurate model idea that calculus shows up in. I could have done this without any calculus at all because this is a straight line, its area is a triangle. I know the formula for the area of a triangle. But that's why the econ books use straight lines. Questions? We did a lot of taking derivatives in business applications back in chapter 3. So we had marginals. The derivative of a cost function was called marginal cost, where this x was units. And then the same thing was true for revenue. And profit. But it turns out that actually finding marginal cost and marginal revenue and marginal profit in a business setting is easy. how much would it cost to make one more thing today? If I am working in a shoe factory and I say I want to go from producing 100 shoes an hour to 101 shoes an hour, do I need more people, more machinery, some sort of incentive to make people work faster? I can figure out the cost to do that. That's a marginal cost. Once I have a marginal cost, I can then say, oh, what I really want to do is integrate that marginal cost and figure out the total increase in cost, not to go from 101 to 100 to 101, but to go from 100 to 200. I look at my gross increase in cost. Now, maybe that marginal cost depends on how many things are being made at a given time. So rather than just being a fixed number, it's a function of X. And then I'm looking at exactly the same sort of analysis we just did for our supply and demand equations. Marginal analysis is a big part of business applications, but you're not all business people. So let's change applications. Questions? The reason I wore short sleeves today is to show off the bruise from my lab work last week. Blood flow, right? Back in chapter 3, when we were first talking about derivatives, I used blood flow and laminar flow through a blood vessel with Poiseuille's law to talk about blood pressure. So let me go back to that idea. There's a lovely picture in the textbook on Poiseuille's law. Back here in chapter 3. Here we go. Page 230, example 7. Here we have blood flowing through a blood vessel. Now, as you can see in this picture, the closer we are to the center of that blood vessel, the faster things are moving. This again is an assumption of laminar flow, that there's very little turbulence, but that's what's causing the slowdown at the edges, the interaction between the blood cells and the fluids with the cell walls themselves. By the way, this is the reason that arteriosclerosis is a problem, because that both narrows the vessel and it creates more turbulence by causing accumulations and buildup along the edges of the vessel. But we end up with this velocity equation down here called Poiseuille's law. And it says that the closer you are to the edge, the slower you're going to go. But let's suppose that where that ring is right here, I want to measure how much blood is going past that spot. Well, it turns out that that can be measured by taking the speed times the area of that circle. And so we get what's called the flux in a blood vessel. And flux, we'd measure by adding up how much went past in the slow area, how much went past in the little faster area, how much went past in the little faster area, and faster, right? As we go in, it's getting faster. So I get this sort of Riemann sum volume here, son of a, it's an integral again, isn't it? the flux moving past a particular area, pi r to the fourth. Why is it to the fourth? Well, there was an r squared in the original problem, and then we have to multiply by that area, so there's another r squared. 8 eta L. Eta is viscosity. This is why people end up on blood thinners. If your blood is too thick, the bigger that number is, the slower things are going to go, right? Same thing with length. Longer vessels take more time to get through, so we need to take all of those pieces into account. All right. So what? Well, I mean, I already did one integral to figure out how much blood is moving through a particular area. How well is your heart working? I've got a little monitor going on telling me about my heart rate, right? How well is yours working? How do you know? The reason I throw this piece out at you is not to be morbid. My parents are 82. They're old people. My uncle, 75, has been having cardiac output issues. His heart isn't pumping very well. And so they actually want to measure how much blood is being pumped through his body. Ta-da! So here is my picture of a heart. 4 chambers, basic biology, right? How's it work? Y'all own one. How's it work? Not an insignificant question. I'm going to find all of your bio teachers and make them smack you upside the head. Come on, people. How's it work? Maddie? Talk to me.
It goes in the old blood that's out of oxygen. It gets oxygenated by pumping through the lungs, and then gets circulated to the rest of the body after it's carried.
Okay, so I have blood that comes back from the body, goes to the lungs. I have blood that comes back from the lungs and then goes back out to the body. Each side of the heart plays a different role. We're color coding them blue and red. Blue is for desaturated blood, for oxygen lacking blood. So that comes in from the body through the vena cava, superior and inferior, goes into the right atrium. So it comes in to the top of your heart on the right side. It is then shunted out the pulmonary artery to the lungs by going into the ventricle at the bottom, which is where the squeeze happens and pushes it out. It goes to the lungs. We have oxygen exchange through hemoglobin. It comes back through the pulmonary veins into the left atrium. It is then dropped into the left ventricle and then squeezed out to the body through the aorta, the aortic arch to the upper body, and then the descending aorta down through your abdomen to your lower body. So there are 2 pushes. There's the tops, which fill the ventricles. The ventricles, which send the blood out. And that's the hard one that's pushing it out to the whole body. That's why your heartbeat has 2 sounds. Dun, dun. It's the top squeeze and the bottom squeeze. That's why your blood pressure has 2 numbers. The hard squeeze is the peak. And that's why when they squeeze you with the blood pressure cuff, they're cutting off all the noise. They can no longer hear that hard squeeze. Then they let up. And as soon as they hear that, that's your top number. And then as soon as they hear the bottom one again, that's your bottom number. Systolic and diastolic. How do I know how well your heart is working? I take an amount of dye and I inject it into your bloodstream. And I inject it right here into the right atrium. And I have to wait for it to clear here, because that's one full cycle of your heart. It went from this here out to the lungs, back in, and then back out through the aorta. So I put this amount of dye into the right atrium, and I wait. I don't see any dye in your aorta. Now, this is done laparoscopically, thank God. I don't have to rip your chest open and saw through the middle of your chest bone to see your heart do this. I do it all laparoscopically. But I know how much blood is moving because of the flux equation. I know the diameter of your aorta. I know the radius of that vessel. I know how long it is. I can measure the distance from the ventricular ending to the aortic arch. I have the length. I can measure the viscosity of your blood by taking a sample. So if I know how much dye I've injected into you, then I can measure the efficiency and the amount of fluid that moved through your heart. The amount that goes in can be measured by the volume coming into the right atrium. The amount that goes out can be measured by the amount coming out through the aorta. That's called the cardiac ejection fraction. And when that is low, your heart is not working very well. It's not getting as much blood out as it should. When that's nice and high, you have a nice, healthy blood pumping system. But if I'm doing this, I've got to look at all of that dye over time. So let's suppose that it takes a certain amount of time to clear the dye in the aorta. Now, we could measure that in seconds, minutes, hours, depending on the amount of dye we put in, but there's a concentration function here. And by the way, that is actually how they do this laparoscopically. They don't do it visually. They do it with a sensor that is chemically tied to the chemical in the dye so that they can measure the concentration of the dye with this little wire indicator. They don't actually need to put a camera in. Well, then I can take the integral and this is actually measuring the amount of blood if I also multiply this by that flux that we had earlier. Now, A can actually be measured. I can measure how much blood comes out of the aorta. The concentration can be gotten at all sorts of time intervals off the end of this probe, which means I can get a table of values to give you this integral. I can use all my numerical methods. I can use Simpson's rule. I can use the midpoint formula. I have a nice numerical way of doing this. And then, rather than using this theoretical calculation for flux, I can calculate actual flux by measuring and dividing. I am not a cardiac expert by any stretch of the imagination. On the other hand, Westinghouse Research Labs in Churchill had an R&D lab devoted to pacemakers. Guess where my father worked? When we moved to Florida, he worked for Cordis Pacers down there in Leeds and Development. So I got to see this stuff as a kid. And then I got to see it as an adult when I thought I had a heart attack and went in for testing, and it sucked. But this is what they actually do to do these integrals. And again, I would love to tell you that this is a theoretical idea and calculus is not useful. But every single cardiology office on the face of the planet has this sort of information for just this reason. I don't know if you're going to be in biology. I know some of you should be. Miss Future Doctor here wants to go to LECOM. Absolutely. Y'all should be doing this sort of stuff. Those of you who are going into business, great. Those of you going into sciences, great. I want you to be doing this. It's going to show up somewhere. Those of you going into math, I have another one for Monday. That's for me. That's going to take our integration idea a little further in a direction I didn't know that many of you might not know about yet. I want to talk about probability from a calculus standpoint. But that's for Monday. I heartily recommend you read through the examples in this section. They will do a very good job. There are a lot of interesting exercises beyond the ones I've assigned that have different situations. One of the ones that I think is a very interesting one is about rumor spread. How fast does a rumor spread? Well, that's a rate. And if I want to look at net change, that's an integral. But I can take that same exact equation, and instead of talking about a rumor spreading, talk about an infectious disease spreading. Ladies and gentlemen, I give you the COVID protocols. If you're interested in that some more, there is a model for infectious disease transmission called the SIR model that gets covered in differential equations courses. It's a lot more about the feedback within a loop, susceptible, infected, recovery. There's also a reinfection model available as well. But that's for epidemiology. So I will see you all on Monday. I hope you have a wonderful weekend. And look, we're early.